All right, hello everyone. We are quickly going to review accumulation with an equation, and in fact we have two equations because this is in and out accumulation, where we have a rate in and a rate out. So both are happening at the same time, which means we're going to have to work with two equations at the same time. So here is a typical, very good first FRQ to remind ourselves how this works. I also have my calculator. You're going to need your calculator for this. So I'm going to do it not with Desmos. If you watch the Calc AB videos, I do everything with Desmos, but now that we're back in person and all that, we need to be good with using our graphing calculator because the AP test requires graphing calculator. So we have the rate at which rainwater flows into a drain pipe is modeled by the function R, where R of t is, there's the rate. And that's your rate in. So this function R of t is your in rate. The pipe is partially blocked, allowing water to drain out of the other end, and this is your out rate. Pay attention, they're both rates. Sometimes they are total amount functions, but in this case, they're both rates because they say rate and cubic feet per hour for both. And then they tell you how long, from 0 to 8. Sometimes we have problems where they're not the same interval. One is 0 to 8, the other one could be 4 to 8 because it doesn't drain out the entire time. So pay attention to that. And then lastly, we have this right here, our initial condition, 30 cubic feet at time 0. So pretty standard in-out accumulation problem. All right. So what does it want me to do in question A? How many cubic feet of rainwater flow in? Just in. It's not asking how much are in the pipe. At time 8, it's not asking rates. It's asking how much total that flowed in. So in part A, this is a typical part A, all we need to do is accumulate from 0 to 8 of your rate in function, which is R of t dt, and that is literally all they're asking for in this question. So you go to your calculator, y equals, remember we plug the function in here, so it is 20 sine of x squared divided by 35. Make sure everything's plugged in correctly. We might as well plug the out function in too because we're going to need it later. So the out function is negative 0.04 x cubed. At this point, you can probably skip ahead while I do all this, but just getting used to plugging into the calculator is a good idea. X squared plus 0.96 x, and that's it. Now, this is t, this is x, not a big deal. It doesn't make a difference because the variable they're talking about in the problem is time, and we're just using x. It's almost like x is t in this problem. Okay, so quit out of this, and the way this works, if you didn't do this last year, we math 9 from 0 to 8, and we're not going to retype the function here. We are going to use the variables, y variables, function y1. We are accumulating the function we have stored in y1 from 0 to 8. Enter 76.570. Now, something new for us this year that I did not talk about last year. After grading the AP test, I realized how bad people are at rounding and how awful it messes them up because they either round too early in the problem and get the wrong answer or round too late. So here's a hack I learned. Just keep 5 decimal places always. Because here's why. I learned that the grader will cut you off at 3. So this answer, they will see 5 decimal places. They'll read the first 3 and stop, and you're golden. And that just, rule of thumb this year for me is going to be always keep 5 decimal places, always. Because I got really tired of seeing students round early in problems, carry that number, and then they were too off in their final answer. Because people are like, well, you said round to 3 decimal places. Yeah, at the end of the problem, not in the middle. So long story short, I'm just going to say 5 decimal places always. Just keep 5. You're going to be right if you keep 5 decimal places. Does this want units? How many cubic feet? This is cubic feet. Because we've accumulated the rate, and that's our total that came in. That's not the amount that was in there. That's the amount that flowed in. All right, B says, is the amount of water in the pipe increasing or decreasing at 3? So to find the rate, because it's asking increasing or decreasing, it's asking is the amount increasing or decreasing, we need to work with the rate functions. So essentially all we need to see is what's bigger, the rate in or the rate out at time 3. So there's kind of 2 ways to do this. You can do the rate in minus the rate out at time 3. And if you get a positive answer, that means more is flowing in. If you get a negative answer, that means more is flowing out. So we go back to our calculator, and I like to do this. In the third function, I like to use the variables function y1 minus variables function y2. And now, if I look at y3, I have the rate in minus the rate out. I can go to the second table set, so second window. And this is a cool feature from last year. Remember, if we set the calculator to ask, we can then go to the table and tell the table, hi, I want to know what's happening at time 3. And I get an answer of, let's see the third function, a negative 0.313. So negative 3.3136. Don't forget the negative, which means the water level is decreasing because the overall rate is negative. You would explain that. You'd say because this is less than 0. I'm just reading the answer key to make sure. So by the way, this is already 4 points in the problem. 1 for the setup, 1 for the answer, 1 for the calculation, and 1 for the answer. And these are such standard questions to ask on an accumulation FRQ. Okay. Question 3, C. At what minimum? So what is the amount of minimum? This is our favorite good old candidates with an equation. So you immediately write the word candidates, and we identify all candidates. This is where I do something last year that I don't know if Mr. Yip did, where I create a total function. So I like to do something like this. Let T of T be the total, whatever this problem is dealing with, amount of water, rate at which rainwater flows into and out, total amount of rainwater in the pipe. So I'm just going to let T of T be the total amount of rainwater. Why do I do this? So that when I'm doing the candidates, I have an easy way to talk about the candidates. So the candidates would be T of my endpoint. I'm going to have to find that. It's going to be T of my other endpoint, whatever, 8. Now, how do you find the internal candidates in an in-out accumulation? Well, this is where the nice part about having the calculator, the y1 minus y2 function, think of that as like the derivative function because it's your overall rate and the derivative just means rate. So if I just find the roots of that function, those are going to be your internal candidates. So that's where I like to unselect these two, go to my window, set the min to 0, set the max to 8 because that's our interval. And then look, my Y window, I make it pretty small, and I just see how many times this thing crosses the x-axis. And we look, and my first candidate, bam, is right there. And my second candidate, does it hit ever? Nope. So there's only one internal candidate. Now let's talk about this. This is the rate. So it looks like because the rate was negative overall, more water was leaving than entering. And then right here, that's my minimum, more water entered than left. So I'm guessing that this is going to be my minimum. But again, do the candidates approach. So let's find this value by doing second, calculate the 0. We go to the left of it, enter. We go to the right of it, enter. And then we hit enter a third time. Not very intuitive, but this is how the calculator works. And that gives you your internal candidate of T of 3.27165. 5 decimal places. So we have identified the 3 candidates. We need to find the accumulation value for each one. So to do T of 0, that one's nice. It's the initial condition. It said there's, 30? There are 30 cubic feet of water in the pipe. So I already have that answer. To get T of 8, this is where you do the initial condition plus accumulation. So you do T of 0 plus initial condition, which is, well, that's T of 0, plus the accumulated rate in, so 0 to 8, R of T dt, minus the accumulated rate out, which is the other function, d of t. I like to keep it as 2 separate integrals because sometimes, like I said, the interval is going to be different for your in and your out. So 2 different intervals here. And then we quit out of all this, and we already have this was the 1. So with this, we can subtract the other accumulation out, oops, math 9, I should just say 9, whatever, minus the accumulation out, 0 to 8, and our out function goes here. Variables, y variables, function, y2, bam, dx, enter. And then we add our initial condition, which was, how do I get a negative value here? Hold on. Let's make sure I stored this correctly. Negative 0.04 t cubed plus 0.4 t squared plus 0.96 t. No, that's right. Let's try this again. Math 9, 0, 8, out function, which is variables, y variables, function, y2, dx, enter. So minus 58. Okay. Yeah, I don't know why it was giving me, that's weird. So I add, this is my out rate, or the out rate accumulated. 76 was my in. So to get the final answer, you do these three pieces. You do 30 plus all the water that flowed in, 76.57035, minus all the water that went out, 58.02666. And you get your answer, which was, I'm not going to calculate it, I'm just going to look it up. 48.54. 48.54368. Don't even have to worry about rounding that last. I don't care if it goes up or not. Just carry to 5 because, like I said, they're going to cut you off at 3. So that's cubic feet. So we would do the same thing for this one because that's our internal candidate. And I'm not going to do the whole calculation, but you know how the setup would work. 0 to, but then you're bound. This is where it's super important you don't round early. So you actually keep all 5 decimal places. And then same with the bounds here, 3.27165, the rate out. And when you do this, oops, DT. When you do this, you get an answer 27.9696456. And that's your winner. Now, you could have almost explained yourself through this, that this had to be the min because the rate function went negative and then went positive. So it had to be, but don't. Do the candidates. It's such an easier way to get the points on these problems. Candidates testing is by far the most important and best way to do this. All right, last question. We'll come over here. The pipe can hold 50 cubic feet of water before overflowing. For t is greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Right, but do not solve an equation involving one or more integrals that gives the time when the pipe will begin to overflow. So I want to know when this equals 50, essentially, is what's going on here. So I want to know when the accumulated rate in, so t of 8, plus the accumulated rate in from 8 to whatever time this occurs at, of the in function. I'll get to this in a second. Minus the accumulated rate out of the out function. I want to know when this equals 50. Because as soon as it equals 50, it's going to begin to overflow. So I would want to find how much water was in the pipe at time 8, which we already did that, because it's saying that this happens after 8 for t is greater than 8. So we have that value. I think we could just say, sure, let's write it in. 48.54368. But now look, I created 2 accumulation functions here where I'm basically saying, okay, there is a time that I don't know where if I were to plug in, let's say it's at time 10, that's when all of this total left-hand side is going to equal 50. So the variable in this problem is not in the integral, it's in the bound. That's where we use that idea of a dummy variable down here. And we can't use t because t is the variable we're using as the value we plug in. So we're just going to use x in our integral functions. Small point, but pretty important. You can't use t here because then it would look like you're inputting into this, but no. we want t to be the variable that we're trying to solve for. And our calculator can't do that. That's why they say set it up, but don't evaluate it. Although I think they say actually right between someone is time w. Oh, so look, they want us to use w. So actually, we could have got away with keeping t here. Oops. So let's get rid of this. So we could have just done this. dt, dt, t, t, because they wanted it to be the time w, where the water is going to equal 50. So had they said time t, we would have made the bound t, and then we couldn't have this variable be t anymore because the input would have been t. Small point, we'll continue to see that. But overall, there's lots going on in this FRQ. This is a very, very, very good one to work your way through and know how to use your calculator and know how to set up a total function and know how to do the candidates testing and know how to find the internal candidate. Lots of stuff in this FRQ that we did last year, and hopefully you saw in Calc AB, but definitely going to see pretty regularly from me this year soon. All right, I think that's it. Okay, good luck with the homework.